Hello. One of the first things that you have to talk about when you're talking about physics is kinematics. Kinematics, think of what kinesiology is or kinetic means. It's all about movement. And so that's what our discussion begins with today, is how do things move and how can we describe them mathematically? It doesn't sound like it's a terribly interesting project, but it really, really is. And you get to use all kinds of skills that you learned in your math classes. Before we can start talking about movement, we have to talk about where do things begin and where do things end. And for that, we need to discuss what's called frame of reference. Now, the frame of reference of something is not that. That's just a frame. And yes, I'm referring to it, but it's not a frame of reference as we regard it in physics. No, in physics, a frame of reference means your choice of coordinate system. The choice of coordinate system means where do things begin? What's the origin, in other words? Think of it as that place where the x and y axes intersect, that's the origin. Or 0 on a number line, that's the origin. So where do things begin? Did you start at your house? Did you start in Ohio? Did you start on Earth? That's the origin. But you also need to know what a positive direction is. If we're talking about one-dimensional or straight line motion, you only need one positive direction. It might be east or up or something like that. But if we're talking about two-dimensional motion, such as on a tabletop, then you need maybe an x-axis and a y-axis. And out here in the real world where we deal with three-dimensional motion, we need x, y, and z. So we have to choose our positive directions. And by the way, that choice is simply one you have to stick with, but it's not necessarily fixed. You could choose, for example, either up or down as a positive direction. So if we're talking about linear motion, that might be the positive direction, with the origin being right at the initial point of that little segment there, which is called a vector. The origin might be right here, but it might not be. It might be right here, with the positive direction still being to the left. On the other hand, if you're talking about an object that's falling, for example, or being thrown into the air, you might have up as your positive direction with the ground as the origin, or maybe the top of a building as the origin. However, if an object's thrown through the air, like a baseball, typically you're going to need two positive directions. We often designate this one X and this one Y, but it doesn't have to be that. Whoops, that wasn't so good, was it? But it doesn't have to look like that. That's just typically what we do. Once we have our frame of reference established, now we can talk about the fundamental ideas of velocity and speed. They seem like they're the same idea. In fact, typically when we talk about speed and velocity, we're talking about the same thing. But that's not quite true in physics. You see, average speed is defined as the total distance traveled divided by the total time it takes to travel. Speed, you see, is a scalar. It doesn't have any direction associated with it. Your car, for example, has a speedometer. It measures how fast you're going. It doesn't tell you what direction you're going. If it told you both, then I guess it would be a velocitometer or something like that. And to calculate speed, we take the total distance that you traveled and we divide it by the total time. Okay? On the other hand, average velocity is the total displacement divided by the total time. And you can see those vector symbols right there, indicating that in fact velocity is a vector, but that's okay. We expect velocity to be a vector because you see right here, this thing, displacement is a vector. Remember, it's change in position, final position, minus initial position, divided by change in time. Typically, we just call that t. Now, to distinguish between the two, let's suppose that your origin is right here, and you take kind of a meandering voyage, maybe down in this direction, then over this way, then up this way, and around here, and you finally end up right there. X marks the spot. You found the treasure. That total path length followed right there is what we call the distance. And that distance divided by the time is what gives you the average speed. On the other hand, if we take the shortcut, the direct path from here to here, That's the displacement. And that displacement divided by the time is going to give you the average velocity. Not only will the velocity have a direction, but in this particular case, it's going to be a lot smaller number than the speed, because the displacement, which is the direct path from where you start to where you finish, is much shorter than the distance. Get it? Here's a weird example. Let's suppose we're talking about the Earth moving around the sun. It generally follows kind of a circular path. Okay, I know it's really elliptical, but we'll call it a circle because it's pretty close. It only ranges from about 91 million to about 94 million miles. Here's the sun. The sun is very happy. In 1 year, the distance the Earth travels is about 600 million miles. So it travels at a speed of about 600 million miles per year, which is 18.5 miles per second. Yeah, tick tock. We just traveled 18.5 miles on our journey around the sun. On the other hand, in 1 year, the Earth ends up back where it started relative to the sun. So its average velocity during that 1 year is 0, because it had no displacement, no change in position relative to 1 year earlier. Now, in a half year, the Earth would end up over here, and its velocity would not be 0. Get it? So they really are different ideas in physics land. If an object's moving at constant velocity, then that constant velocity is just the displacement divided by the time. If we take that equation and solve it for position, we get a formula. X equals initial position plus velocity times time. That is called the equation of motion. Anytime you have an equation that tells you the position at a given amount of time, that's an equation of motion. And this is the simplest equation of motion, one where you are moving at a constant velocity. It tells you how to get to the new position if you know the original position, the velocity, and then you have a formula so you can plug in any time that you want. Got it? We're going to use these ideas to work a problem. So let's suppose that Julie walked 12 meters east in 3.23 seconds, paused for 2.4 seconds, then walked 25 meters west in 7.9 seconds. Find her average speed and average velocity. Well, let's see what we have. First, we choose our positive direction. East is positive. We also need to choose an origin. The origin is pretty obviously going to be where Julie started her walk. That makes sense? List all of the variables about which we know things. We know her first displacement, I'll call that delta x1, was 12 meters, and I just leave it as 12 meters. I don't have to write east because east is the positive direction. That took place in a time of 3.23 seconds. Then she paused for 2.4 seconds. I won't bother writing a displacement. And then after that, she traveled negative 25 meters. What's that mean? 25 meters west, because east is the positive direction, in a time of 7.9 seconds. But I also like to list the things we're trying to find. What's her average speed and what's her average velocity? And so that's what the problem that we're going to work on. Let's see if we can set it up. Let's start with average speed. If we want to find her average speed, we need to find the total distance divided by the total time. Well, her total distance, remember distance is a scalar, not a vector, is 12 meters plus 0 meters plus 25 meters, not negative 25. The minus sign has to do with direction. She moved 25 meters. Divided by a total time of 3.23 seconds plus 2.4 seconds plus 7.9 seconds. And so we get 37 divided by 13.53 seconds. When we divide that out, you get an answer of 2.735 and a little bit more stuff meters per second. Now that needs to be rounded because we don't want to imply something that we don't really believe, that we know the answer to the nearest thousandth of a meter per second. This had 2 significant figures, this had 4. Remember, chain is only as strong as its weakest link, and so we round that to 2 significant figures, and our answer is 2.7, don't forget to put a unit, meters per second. Go ahead and circle that since that's a good final answer. But what about that second question, the average velocity? Well, the average velocity is going to be the total displacement divided by the total time. Displacement is a vector, and so that means we will have to consider positives and negatives. So we would write 12, I'm going to skip the plus 0, plus negative 25. Now that's our total displacement. The total time is the same as it was before. It's still 13.53 seconds. Just so this doesn't get too confusing with the signs, maybe I'll put this in parentheses. So you can see I'm adding 12 plus negative 25. That means when we do the problem, we get an answer that in fact is negative. Negative what? Well, negative 0.961 meters per second. Again, round to 2 significant figures, so it's negative 0.96 meters per second. Now, what does that minus sign mean? Well, don't forget when we established our frame of reference, we said that east is the positive direction. And so that negative means that the average velocity is to the west. And it's also a different number than the speed. Let's see if we can figure out why. You see, what happened was Julie walked to the east 12 meters in a certain amount of time. Then she turned around after waiting for 2.4 seconds and walked west 25 meters. And so she ended up here. Well, remember, when you add vectors, you go from where you start to where you finish. We started here, or Julie started here. She finished over here. So the straight line resultant vector would be like that. Yeah. Effectively, she was moving west pretty slowly because it took her a long time to take the trip. And so that's the difference between speed and velocity, and that's how you work a physics problem. You set up your frame of reference, you list your variables, including the ones you're trying to find, and then you find the appropriate formula to answer the question. Got that? Next time we'll look at a more complicated kinematics problem, and so I'll see you then.